All right, welcome. Hoon School Live, lesson 6, is that right? Yeah, lesson 6, which is the 7th of 8 total. And I think today will be a little bit lighter. We're mainly going to look at the standard library, some of the operations that are built in. If you've started working with a programming language before, then you've definitely run into the issue where you just need to know what's actually in the standard library. And Hoon has a pretty good standard library for certain kinds of operations. There are some surprising gaps, which are partially explained by the kinds of things Hoon is designed to do and the kinds of things that have not been on the mind of anyone. So for instance, Mopful, Winrux, and I are working on a mathematical algorithms library. Since as of right now, there is no sine or cosine or exponential or some of these other operations that you might expect to have in a math library. And there haven't really been numericists working on or using Urbit up to this point. So that's not particularly surprising that would be weaker. But there are a lot of operations for working on lists, data structures, a lot of things for web operations, converting data types one between another, reading text into Urbit data types, converting Urbit types back into written text. So we're going to start off there today, and then we're going to go delve into manipulating functions and building new kinds of gates out of old kinds of gates. So if we have a gate that does one thing, we can modify it. We can do things like change its sample or change its behavior, basically live, right? Like we can actually modify the gate itself and get a new characteristic behavior out of it. Let's go ahead and start with a fake sod, as is customary. And get all this junk out of the way. And keep the chat visible here. To me, but not in your way. All right. So whenever we run code in the dojo, the subject is going to make available to us a standard library. There are libraries that we have seen how to import when we are building generators, for instance, and when we start building apps in App School Live, we will very often build and then include libraries as well. But at least when you're doing dojo work, it's fairly uncommon to import libraries because the standard library does a lot of things for you and it is immediately available to you. Now, the Hoon has been built to do is to parse and build code. So a lot of the operations by number, right, by volume, are intended to parse text and build code. But there's a lot of other convenient functions that are tucked away in the Hoon, what we'll call the Hoon subject. Sometimes about subject-oriented programming and how this means that basically we have there's a binary tree at any point inside Urbit that, I may have miscounted my values here, but you get the idea that everything inside of Urbit lives inside of this addressable tree that contains data and code at various addresses in it. And what we have is a system where every part of Arvo, which is the main event handler, is actually accessible to you and visible to you, and you're able to interact with it and work with it to build certain things. So if you were to go to sys and your fake sods peer inside of your file browser, then you'd be able to see the files that are present there. So we'll actually do this here with the ls generator. Actually, before I even do that, let's talk briefly about paths. Every path on Urbit starts with the ship identity as text. So that's a pat TA, that's a not. the desk name, and then the timestamp that refers to the current place. And we can actually build this manually like this and still, get that information. I guess I don't need to do the .sig because that automatically gets included there. But I could build it manually by specifying these things. If I use the equal signs, the TISs, then it fills in what the standard values for that would be, which is your current ship identity, the current desk, which is typically base, and then the timestamp, which refers to now. So whenever we want to refer to a file in Urbit's file system, we start the reference with the ship we are on, the desk we are on, which is the particular collection of files that we're working with, and the timestamp, which means basically the most recent collection of files. It's a version controlled file system like Git or GitHub. So there's actually a lot of interesting things you can do with Clay, which is the Urbit file system. But for right now, we just need to be able to look at a particular directory inside of it. So we're going to use the ls generator and run fazls on sys. So we see here that there are, I guess this list is 5 files, which is kind of interesting because of that Kelvin, but we'll elide that for a moment. So there's an arvo.hoon would be the way that your regular host file system would express it. Here we're using the file type divided by a slash because that's the same kind of thing that separates elements of your file system path anyway. So Urbit just thinks of every divider in a path to a particular resource as a slash. So there's an arvo, there's a hoon.hoon, there's a lol.hoon, there's a zeus.hoon, and then there's a vein directory. So arvo.hoon is essentially your event handler. It's the actual operating system that processes things that take place. Every time you type something, every time you, interact with an agent, every time you send a message in groups, every time you have an action in one of the other apps that you've installed, Arvo is the handler for that. It's basically a dispatcher, right? It's an operator. It's the part that sits at the core of everything and tells a message to go from one part of Urbit to another, from one agent to another, from one agent to a vein, which is one of the system operations. Hoon contains the standard, the language fundamentals for the Hoon parser and builder. Lol is a file that contains structures and services that are necessary in the boot process. So they're necessary to bootstrap Arvo for the first time. And Zeus is the variety of data parsing and data representation structures as well. If I were to look inside of the vein directory, I would see Ames, Bane, Clay, Dill, Air, Gall, Irish, Jail, and Con. These are the veins of the Urbit system. These are essentially system daemons. These are processes that run continuously that handle different aspects of the way that Urbit operates. So Ames is your ship-to-ship networking. Bane is your system clock that handles events and event wake-ups. Clay is your file system. Dill is your terminal, your keyboard handler. Air is your HTTP vein. It's the one that acts as a server when you serve a ship, when you access Urbit through a web browser, everything is going through Air and the system, the set of tools that are present there. Gall is your app handler. So anytime you're running an agent or an app on an Urbit ship, this is going through Gall. Iris is your client vein. It's where Urbit acts as a browser, like when it looks up something on the internet. Jail is your cryptography, your identity, the things your private key, and so forth. And then Con is a control vein that's useful for external commands from Earth to Mars, as it were. We're not going to spend much time directly interacting with any of these, except that Dojo, for instance, that we're running, is running in Gall. So Gall is your user space. It's running the actual apps and agents that you're using on a day-to-day basis. So that's where these things live. That's how you're interacting with them. What we are mainly interested in is the kinds of tools that are provided by Hoon and Zeus. I'm not going to draw a big distinction between these, except to say that, they're both provided by the system. If I were to type dot, if you have an old fake Zod, this may spin for a minute, and it may be a problem because it means that there's a lot of things that it's trying to calculate to output. If you have a new fake Zod, then it should just print a single line that will give you some information about what's going on. So for instance, if you type something like add, it'll give you a line that looks like this. If you type dot, which means the current subject, on a fresh ship, it'll give you a very short interaction like this. It'll give you some information. So the rightmost bit, one of the roots of the core that you're looking at, one of the roots of the binary tree, is the Hoon version number that you're running, in this case 139. And then this is basically a hash, a short bit of information that describes the core which you're running at some particular point. So add has a sample, you remember a core is a cell of battery and payload is sample and context. So your core is the is the knock code that you're actually running at some particular point. Your sample, which is at address 6 in the binary tree, are your inputs, the things that are coming into your ship or to your core. And then your context, which is the subject, which is the things that this particular gate knows about, are included as these values here. Now, we know already that there are things like addition, and there's a decrement, which decreases a value by 5. There's a knock command, which increases a value by 5. You've probably at this point run across things like modulus, which is remainder after division. So if I divide 15 by 4 and I keep the remainder, then if I divide 15 by 4, then I get 3 with remainder 3. So that's what the modulus tells me. And I could also do division with remainder of 15 and 4, and it would give me both of those values as a cell. There are things we can do, like we've talked a little bit about cells. All right, so we put a tick in something, we get units. We get a unit as a cell here. So remember, a unit is a thing we use with a map or a set. Anytime we need to look up a value, because we need to be able to distinguish between a value being 0 and a value being like a value not existing. So a unit lets us do that. So if we have a head tagged cell, it is effectively a unit. There are a lot of operations to work with units. Some of them modify gates to work with units correctly. Some of them are like need. So if we have something, let's come up with a map. Let's see, I guess we had some maps from lesson 5, didn't we? Let me copy one of those and I'll share it with you as well. Colors was my favorite of those. All right, so we have a colors map. So if we were to say get by colors green. So you remember this first part is generating a gate that operates on colors, on the map colors. And then we are applying that gate to the value green, which is effectively a key lookup. Okay. Now, one thing we can do is, because we get a unit back, but we want the value, there is an arm, or there's a gate called need, which requires that the value exists, and it will crash if it does not, but it returns to you the unwrapped value. So you don't have to actively think in this case about opening up the value and unwrapping the value. On the other hand, if you look for the name of a value that doesn't exist, you'll simply get a crash, right? Like it fails to parse. Nothing happens as a result of it. Some of these are specific to particular types that are deeper in the system. And this, so we have things like cuss, which is our uppercase for everything. We have cas, which is our lowercase. Some of these are meaningfully named, like we have run into chord rip. We often say crypt, but we mean chord rip. We mean like take the contents of this tape and turn it into a chord, turn it into a PAT-T. So, a tape, of course, is a list of bytes. It's a list of ASCII characters. And a chord is a serial representation in memory, right? That these characters are actually in memory. Hello, Mars. Some of these are whimsical. Cuss is a little bit whimsical. So crip has a good mnemonic. Chord rip, tape rip is trip is the other way. Cuss is whimsical because you're turning it into all uppercase, which means you are shouting in 90s internet slang. Cas is one you just have to remember, unfortunately. There is an obsession in the Urbit Standard Library with 4-letter names for things, and in some cases 2-letter names for things. But we are simply stuck with that. There's not that much we can do about it. We have to live with the consequences of this decision. It's not that bad, if you're thinking about comparing to like a Microsoft API or something. You might have something like retrieve value by key as string. Like that's also sort of hard to remember in a sense, in that there's a lot of English language phrases that would pattern match with this that would still map to the same thing. So I don't want to excuse the impenetrability of this too much, but I do want to recognize that there's a sense in which you have to memorize any standard library that you come up against for the first time. Some of these are buried in other cores. So if I want to do some kind of operation, sometimes I have to go poke around and see if I can look this up in something. So let me see. We have, if I remember correctly, this might be in format, but there's an HTML core. It has a D inside of it. And I can give it, some value. Let's see if that worked. Jack, do you remember offhand how we convert an HTML? This is one I didn't have an example ready to hand. Not inside a format. Well, anyway, sometimes you run into these cores, but there are parsers for various things. So for instance, here's one. Oops. All right, so what does this one do? So there's an HTML core that has a MIMES core inside of it, that has a base 16 core inside of it, which is for hexadecimal operations. And in this case, typically these are organized as EN for convert to, and DE, day, for convert from, like encode, decode, I think is the mnemonic they're aiming for here. And so this one is taking a hexadecimal string as bytes, right? A byte is 8 characters, it's 2 to the third. You will often see powers of 2 expressed in Urbit simply as the power to which the 2 is placed. So if it was 256, then it would be 8, right? 2 to the 8th. So in this case, 2 to the third is bytes. If I were to change that to something else like a 4, okay, now I see what that 4 is doing is it's actually 0 padding, right? Like what's going on here. Oh, it's DXML, that's right. Let's try this one. Well, it's something. Anyway, I don't want to spend my whole life trying to do it. Oh, maybe it's in XML. Oh, good grief. Yeah, this is the problem, is sometimes you end up with these Urbit commands that are like a little bit crazy. This one, oh, that wants it as a chord. Maybe that's what's going on. Okay, there we go. So this is, some platforms, when they represent HTML, if you think about HTML and you have nested tags and they have to stack, you step in a certain number, you step out a certain number, and so forth. It is not uncommon for systems to want a representation other than HTML to show HTML. Clojure does this, some other languages do this. So internally, when they are processing things that are HTML, it doesn't look like HTML. What Urbit does is it has this, you'll notice at the first place that this is a unit because it could fail to parse, of course, which would be a return a null. And then it is producing this P cell that has no attributes and has the contents of hello in this particular case. So that's what that example is there. All right, back to something like this one. So it's 0 padding it by number of bytes. If I were to give it three characters, then it's basically saying, consume 3 bytes of this. If I were to give it 2, it's going to consume the 2 rightmost bytes in this particular case and do these kinds of operations. There's also operations to go the other way. So in this case, I want to, let me reconstruct this. So D base 16 HTML. All right, so this gives me a unit. Then it gives me the byte width, and then it gives me the value, in this case, as a PAT-UD. So if I want to see this as a hexadecimal value, I need to access address 7, which I can also access by saying I'm moving to the right in the cell, which would give me this cell in relative notation, and then to the right of that, which is this value here. You'll notice that the face Q, the value that's associated with this, I can refer to that explicitly. I can resolve that against the subject to the right hand of it. Or like I do here, I can just ignore it. And when I do the value transformation, it goes away. It doesn't carry in. So faces are nice because they're a little bit more flexible with variables and they can be added or dropped at will. And you're still working with the underlying value in any case. Let's see, there are tools for working with like Bitcoin wallet base 58 with JSON strings, HTML, XML, basically all of the common formats that are used on the modern web have operations that will do different conversions between them. Some of you may have run into this. It's probably the most common case now where you write text as markdown, and then you are referring to some website like Wikipedia, Um, I just made this up, computing as a service. All right, and you'll notice that this one correctly matches those parentheses, but in general, those parentheses would not be matched correctly by a markdown parser. The first parenthesis would match to this parenthesis here, and you'd have this. It would actually form a URL that is missing the rightmost parenthesis. And so if you click on it, it takes you to a website that's wrong, for example. And so the way to get around that is to convert this to a URL safe type. So in this case, I could say computing as a service. And you'll see it converts the PAL and PAR, the left and right parentheses, to a %28 and %29. So that's the standard URL safe way of representing non-standard characters. So, URLs in a browser often resolve internally to, if you type the URL in your address bar, not every character is a valid character to actually locate something. There's a specific subset of ASCII that is defined as the standard subset. And so that's what's taking place here. What I've mainly started to show you here is just that, we have a lot of tools for converting numbers back and forth from text to values and from values to text. More of these are listed in the standard library. There are interesting ways to modify programs, right? So, if we've done something like add 3, we can't do this, right? We have to do this somewhat more awkward case where we're what we're really doing is a senhep, and our senhep is accepting an add and then a colhep, right? A pair of values. And then on the, what we actually need is a 3, wait. This is a cell of 3, and then this is also a senhep. And then this is a colhep. Good grief. These things get deep. See, this is why we're not so mean. We don't make you chart these out after the first couple lessons, because it's good to be able to think like this, but actually like drawing these out every time you want to work on an operation is a little bit of a pain. So if we want to operate on this, functionally, this is what we're doing when we build this kind of expression here. However, as humans, we really prefer to just think in terms of a running sum, right? Like it would be nice if we could modify add in such a way that it just worked to include as many values as we want. And it turns out that we can do this. So if we precede everything with a colon, we precede the function call with a colon, then what we've done is we've taken a gate and we've converted it to operate on multiple values in series. All right, and we could do the same thing with multiplication. 3 times 4 times 5. This is kind of neat. This is a new rune. We haven't had a new rune for a couple lessons. So this is mic-col. So this is to change what we're going to call the arity, or like is it a binary gate? Is it a ternary gate? Is it a gate that operates on 4 or fourfold gate, and so forth? We're going to call this changing a gate from binary to n-ary, so we can operate on any number of values. And I'm actually curious here what would happen if I did add 1. Yeah, so It doesn't care. It's happy, right? I can give it a single value. It'll work correctly. I can give it 2 values. It'll work correctly. I can give it as many values as I want. And this gate will work correctly. So when we are working with standard library functions, presumably not these text processing ones, but some of the others, like the mathematical ones, if we need to modify them slightly to get the behavior that we want, we have some tools at hand that we can use to manipulate the gate, to change the gate, change the behavior, make it pretend like it has a slightly different sample, or it operates on different kinds of values and so forth. All right. Now, in this case, what we've done is we've changed the number of things that it operates on effectively in the sample. So let's see. So let's say ways to change a gate. All right, so the first way to change a gate is change the arity, right? Change the number of values it operates on. All right, so we can change it so it's agnostic, right? So that it does this on any number of values. I better write it this way, because another way we can change the arity is we can reduce the number of values in the sample. All right, so an example of this would be, let's see, we've run through a couple of different ways of solving the quadratic expression. So x squared plus bx plus c equals 0. All right. So one of the ways we did this was we defined a gate, x equals pat ud, a equals pat ud, b tis pat ud, c tis pat ud. And then we returned add mol a mol x mol bx c. That look correct? That looks correct to me. Another way we did this was we could say, okay, well, we're going to define a door which lets us specify the values once. And actually, I better, to be clear, so way one, and the way we use way one is I was going to type this in the dojo and type it this way. So let me give it to you in this shape. All right, there you go. And if I were to operate using this, I would say my gate 2, 3, 4, 5. So the x value is 2, and so it's operating on 3x squared plus 4x plus 5, and yields 25. The next way we do this then is let me call this my door. And my door is a core, and it'll have some, call this quadratic. And this will only accept a pat ud, and then it will do a similar sort of calculation. Like this. All right, and to use my door, first, I would have to build the arm in my door by providing it the values that go in that sample. So that, right, this is our gate building gate pattern again. So we're building the gate, we're building the operation, and then we're applying it to a particular value. So in this case, we do get the same answer. So that's good. We like that. Should give us the same answer every time as long as we're doing it correctly. All right, so that's way 2. All right. I'm going to give you a third way now. All right, turns out there's a lot of ways we can build these sorts of things. So a third way we can build this. Let's see, what's the right way to express this? So let's say we have my gate already defined. And then what I would like to do is I'm going to do what's called currying. I'm going to bind part of the sample. I'll call this my one gate just because it's a single valued gate. And now what I've done is I've built a new gate in which the right-hand part of this sample has been fixed. We call this binding in computer science. So you'll hear this referred to as binding the sample, binding the values in the sample. But what we've done is we've modified the gate by already providing the values which the gate will use. So cur is a gate building gate. And you notice that applied to the right-hand side, to the right-hand values. There's a curry, which is C-U-R-Y, which applies to the left hand of the sample if you need to bind things that way. All right. So we can do some interesting things with this. You know, we can change the number of samples by doing what's called currying to build it. So this is another way to change the gate by curry and curry. We can chain gates together. All right, so what this will mean here is that we can, calls it a cork, but we can cork two gates together. We can arrange gates so that the result of one gate applies to the, like is passed to the next gate. So if I wanted to build a gate like this, let me do Control C because that's going to be kind of gross. This is actually a gate. It's a gate builder. If I go to value like 20. What this has done, maybe I should do this with a value that's a little bit smaller so we see what's going on, is I've chained decrement and the pat UX mold, right? A mold is a gate. It's a type, right? It coerces it to a type. I've chained these two gates together. And so here, first the value is decremented, 8 goes to 7. And then that 7 is passed to the pat UX and becomes 0x7. So I can chain gates together with cork, or if I want to do it in the other way, I can do coral, which goes the other way. So I can use that to build a pipeline of gates in which each one is applied in order to modify a value as I'm producing this value. Just kind of a neat thing to do. Let me see. Let's see if I want to operate on a list. All right, we've seen turn before. What did turn do for us? Remember turn? Does anyone remember turn? I think we talked about it.
It rolls, or it puts a gate through each entry of the list.
Yes. So in this case, I give it a list and then I give it the mold pat UX and it modifies the list by applying it to each entry. So the result of turn is a list of the same size. All right. Excellent. What we can also do is we can do what's called folding a list. So to fold a list, we can do this with like a roll or a reel are going to be the operations here. This is going to take a list. Let's see if it works here for me. No, it's failing. If you ever get a mole grow, it means you haven't satisfied the typecaster. All right, so what does roll do? It accepts a list and an add. What's it give to me? Gives me the result. Yeah, it collapses it to one value. It's a reduction operation. So it applies the gate that is its second argument pairwise to each thing in your list, and then yields you the result. I guess let's see if it what I want to see here is if it hangs on to type information. And I suspect it will if I don't clobber the type information. No, actually, it gets rid of the type information. Interesting. I actually would have expected it to keep the type information. Curious. Okay. All right, so or we can fold it, apply it across a list of values, and that's roll and reel. Reel is really similar, but reel goes the other way, right to left. And for like mole, it doesn't matter, but for some things it matters which order you do things in. I guess that would probably underflow.
Neil, if you had put the convert to list pat UX outside of the outermost parenthesis, do you think that it would have kept the pat UX?
Okay, so if I had done it outside here,
Yeah.
it would have given me the result as a pat UX. It's just that either roll or mole, and more likely mole, is eliding type information when it does that calculation.
Okay.
Some of you have definitely run into and been frustrated by the fact that some Hoon expressions, like if I turn on a null terminated tuple, it's happy. It doesn't care. It looks like a list, and so it fits. But obviously other things, if we don't exactly satisfy that it actually has list nature, list type, then it fails. And so we have to make sure that we are actually being specific about these values here, which is a little bit frustrating, but it never hurts to overcast. Well, I won't say never, but it almost never hurts to overcast your values, right? Like Hoon likes to know what type it's working with at a particular point. And so, it's good for us to provide that information to it. If we were to do something like add, we can't do that. So I'm going to put a question mark here. Talk me through this. If I wanted to add 1 to each value in this list, how could I do it? I've got some tools here. What's one, I can think of 2 ways offhand here. How would I add 1 to every value in this list?
Well, you would start with turn, right? You would start there.
With earn or turn?
With turn.
With turn, okay, yeah.
Right?
Yeah, so I would turn, and then the list of values wouldn't change. So what would I do here?
In a previous line, you could name add X, like a gate, add X1, and then put the whatever you named it, like add 1 as the gate that turn uses.
Yep. Now, a neat thing about Hoon, and something you'll see happen very often, we can do what you said, but we can actually do it in line. I don't have to do it on a separate line. And Hoon is terse enough and expressive enough that you'll very often see something that looks like this in code, where someone needs a gate to do some kind of operation. They define the gate right there. Okay, what else? Can you think of another way? The other way is a bit trickier. What if I used a curry? Like cur. How can I do it with a cur?
Couldn't you just do cur and then add and 1?
Looks like I can. So if I bind if I bind the sample in add to operate on the value 1, then de facto it's incrementing these values. Now, unfortunately, what I can't do is, I know there's a less rune, right? That there's dot less, like I can increment a value with less, which is the shorthand for dot less, which all the dot runes are knock runes. Unfortunately, I can't quite express it that way, just because the syntax of the language doesn't quite work that way. Yeah, so there's a couple ways. I mean, I could do this if I have enough parentheses at the close, so I could do it that way as well.
I have a question.
Yeah.
I can see what Curry is doing, but I can't, off the top of my head, describe it. What's like a short way of describing like what Curry does here?
So what it does is it takes the list of input arguments like this, and it fixes starting at the right. And then curry, C-U-R-Y, would start at the left if I wanted to bind things from the left. For add, it doesn't matter, right? I could cur, I could curry. It would be the same.
Okay.
But what you're doing is you're freezing part of the sample, which reduces the number of values that you have to give to complete the operation.
Okay, that makes sense. Thank you.
And these are actually kind of neat. Like this is one of the places where Hoon starts to feel pretty powerful, is that we can tersely alter cores on the fly. And although we don't need to get very deep into this in Hoon school compared to how deep you can get into core modification, because ultimately, like a system upgrade is essentially a core modification. You're swapping out part of your core while your ship is running, for other code, which is pretty neat that you can do that. That's what Hoon is built to do. But here, we're able to actually take an existing gate and modify its behavior and use our gate building gate pattern to just produce a new gate that is an old gate with a modified behavior. We've changed the sample, or we've changed the way that it interacts with the number of arguments that it has, or we've chained it together so that we have multiple gates that are applying serially to each other and so forth. So there's some pretty neat parts in what we've seen here. And yeah, it is kind of a Lispy. The syntax that we use is not particularly Lispy here, but it is a lot like what you can do with Lisp. I'm actually working on a blog post for, hopefully I'll get it done by June. I'm working on a blog post that's essentially a comparison of Lisp and Hoon, and some of the things they have in common and places where they deviate. And I think if you have Lisp experience, I think in general you'll find that Hoon's rune expressions are more powerful because they can be terser than Lisp macros, and that Hoon's strong static typing is really helpful. So Lisp is dynamically typed. You know, it just sort of runs the code and see if the code does the thing that you want, and that is powerful, right? Like, there are a lot of languages where you lean on dynamic typing. You don't know what the type is ahead of time. You just try and do the operation. And if the operation succeeds, fantastic, it worked. Hoon doesn't do that, right? Hoon requires you to know the types of everything up front and to specify them very carefully, right? So, you know, for instance, we even have assertions, right? So I can actually assert that some particular operation is true, right? So I should be able to say something like, is 1 equal to no? And if it's not, you know, so this is like a what call, so it'll have 3 children, it'll have a conditional, a case if true and a case if false. So if 1 is equal to no, then I'll say first branch, and otherwise I'll say second branch, just to be clear in what's going on here. All right, so it takes second branch. So 1 and no aren't exactly equal to each other, which is a little bit funny because actually structurally they are, but type-wise they are not, right? So I can actually also say is 1 and 0, 1, are these equal to each other? And they're not, right? The type matters. The type is part of the matching that we're doing in this case. Yes, go ahead.
This is a bit off topic, but just in the general history of these types of expression, like, is this somehow like, because Russell and Wittgenstein were trying to like write logic as really discrete statements. Is this like achieving that?
Are we going back to the Principia Mathematica?
Yeah, a little bit.
So
I don't know.
Yeah, so ultimately, I think the fruit of that, of the Russell and Whitehead endeavor that we should take as normative, is the invention of the lambda calculus. There are a lot of people who did other things that were sort of broadly equivalent. You know, Gödel invented the idea of encoding statements as numbers, and that actually turned out to be hugely important for computer science, because that's what we're doing on the computers. We're encoding statements as numbers. So Gödel invented that, incidentally, in his incompleteness theorem papers. But what we're looking at is, can we write terse expressions that simply express the computational operation that we are trying to do? Hoon does this, but it sort of does this at second order because it compiles to Nock, and Nock is a combinator calculus. It's not a lambda calculus, but it's related. And so when you want to have the very sort of the very short limited set of symbols that require you to do very elaborate proofs like Russell and Whitehead were doing, then you're talking about something that is more similar to Nock, right? And then, as is pointed out in the chat here, there's a sense in which any programming language crosses the bar of being Turing complete, right? Anything that is considered Turing completeness is actually interesting because it's kind of a tautology. It's saying anything computable is Turing complete, but we define computability by Turing completeness, which is an interesting problem, right? But Turing completeness is interesting because it constrained our search space in definitions to a set of problems that can be calculated in the modern contemporary sense that we understand calculation. And knock is not the simplest possible set of operations that could do this, but it's not far off either. There's a sense in which, like, if you've read Gödel Escherbach by Douglas Hofstadter, which I commend to all of you as an excellent exercise, knock feels very, very Hofstadter. It feels like the sorts of languages that he's playing games with in that book. So knock is akin to this, and Hoon participates to some extent in knock nature, but not entirely. So for instance, if I were to zapcom an expression like 0x1 versus 1, Hoon is carrying some type metadata information as tags that allows it to do operations that ultimately wouldn't result in knock. So if I were to compile these to knock expressions, these would actually compile to the same knock. I can have multiple Hoon expressions that would result in the same knock. So knock is more minimalist in that sense. But Hoon, by carrying around type information, gives power in how we are going to write and express things. Now I'm actually curious what it would look like to wrap the yeah, so that's what happens if the result of the Hoon abstract syntax tree is knock, then I get a series of atoms in sequence there. Anyway, does that kind of answer your question? Maybe.
Yeah.
Okay.
Thank you.
One of the problems or one of the challenges with computers versus like Russell and Whitehead is computers ultimately only know about numbers, which is why knock elects to express all operations as the first value in a cell, right? It's a numeric operation. It's knock rule 1, knock rule 2, knock rule 3. Because we can't write, you know, like if I were to do this in text, I could do it, you know, I could say, if 1, because A equals 3, you know, I could even do like a fancy therefore, you know, you can do these kinds of expressions mathematically. Well, I'm only able to do some of these things. Anyway, that don't really have a clean mapping to the language that knock is using. I mean, you could define them, of course, like you could specify computer operations that would correspond to those, but that's not the path knock takes. Knock decides to express everything purely in numeric values or in pairs of numeric values. All right, the notes that I'll give you also has some more on what runes, like I had a what gar assertion there. There's some other assertions and type checking values that are worth keeping in mind, worth having a look at as well. We'll basically clean out the rest of the what runes, the comparison runes, in doing this, which is great because I think that's the only family we're actually completists on in Hoon School, that we actually look at every single one of them. So we'll get that out to you in the next couple of days. Any other questions about modifying gate behavior or the standard library insofar as that goes? All right.